Have you ever looked at a massive skyscraper and just wondered, how does something like that even begin? Well, it's not with a crane and it's not with a shovel. It starts with numbers. In this explainer, we're going to decode the hidden language of construction, that critical first step that decides if a project even gets off the ground.
I mean, that's the big question, isn't it? You've got a blueprint, you've got this amazing idea, this dream, but what's it actually going to cost? How do you turn a drawing into a real dollar amount? Well, that's the core problem that the entire field of construction estimation was created to solve. So here's our game plan. We're going to start with the big picture, then look at how a rough guess turns into a super precise calculation. We'll even check out the actual tools and codes builders use, and then we'll wrap it all up with a quick quiz to see what you've learned.
Okay, so to really understand how buildings get their price tags, you have to get your head around two key ideas that work together on every single project: estimation and specification. Now, they might sound kind of similar, but trust me, they answer two very different and very important questions.
So what's the deal with these two? Well, think of it like this. Estimation is all about the numbers. It's the math. It tells you how many bricks, how much concrete, and what the likely cost is going to be. Specification, on the other hand, is all about quality. It's the written description of the type of brick, the grade of concrete, and the standard of the work. You know, the stuff you can't really show in a drawing. So, estimation is quantity, specification is quality. Simple as that.
Right, so not all estimates are created equal. It's kind of like planning a road trip, right? You might have a rough ballpark idea of the cost, or you could have a detailed line-by-line budget. Well, construction estimates work the same way. They have different levels of precision for different stages of a project. Let's dive in. First step, you've got the preliminary estimate. You can think of this as the back-of-the-napkin calculation, but for a massive project. Its whole purpose is to answer one simple question. Is this project even in the realm of possibility, financially? It's that first quick check to get a thumbs up from the people controlling the money.
And how are these things so quick? Well, they use really broad strokes. The Plinth area method, for example, just multiplies the building's footprint by a known cost per square meter. For taller buildings, they might use the cubic content method, which looks at the total volume. And for something really specialized, like a hospital, they might even guess based on the cost per bed. It's fast, it's approximate, but hey, it gets the ball rolling.
But you know, a ballpark figure only gets you so far. To actually build something, you've got to move from a rough guess to an exact science. You need precision.
And that's where the detailed estimate comes in. This is the master document. This is the big one. Every single item, we're talking every nail, every wire, every pane of glass, is counted and costed. This is no longer a guess. It's a super meticulous calculation. And it's what you need to get the final technical sanction, the ultimate green light to start building.
But what happens when things change? You know, projects are messy, costs shift. In the construction world, there's a critical number that acts as a kind of tripwire, and that number is 5%.
This rule is really all about control. If it looks like the final cost is going to go more than 5% over that original detailed estimate, you can't just keep building. Nope. You have to stop, go back to the drawing board, and prepare a formal revised estimate that explains exactly why the costs went up. It's like a built-in safety check to keep budgets from just spiraling out of control.
Okay, so we talked about the what and the why of estimating, but how do builders actually calculate all those quantities for that big detailed estimate? Let's take a look at the tools of the trade. One of the most common ways is called the long wall, short wall method, and it's really clever in its simplicity. First, you figure out the length of a room's long walls, measuring from the very outside edge to the other outside edge. Then, you measure the short walls so they fit snugly in between those long walls. It's a simple little trick that stops you from counting the corners twice. Now there's a faster, maybe a little more technical way to do it called the Centerline Method. With this one, you calculate the total length of the center line of every wall in the plan. But, and this is a big but, you have to be careful. For every spot where one wall smacks into another, forming a T, you have to subtract half the wall's width to, you guessed it, avoid double counting that material. Can you imagine the chaos if one builder measured concrete in buckets and another used wheelbarrows? To stop that from happening, the entire industry relies on a universal code, a standard that makes sure everyone is speaking the same language. In India, for instance, that standard is called IS 1200.
Now what's really cool here is the logic behind all these units. It's not random at all. You see big, bulky stuff like digging up earth or pouring concrete, that's measured by volume, in cubic meters. But thin stuff, things that are just on the surface, like a damp-proof course or a coat of paint, that's measured by area, in square meters. And steel, because it's so dense, is measured by weight. See? There's a system to it. And here's a perfect example of that logic. A door. The thick, chunky frame, the chaukat, it has depth, right? So it's measured by its volume, in cubic meters. But the thin panel or shutter that actually fits inside the frame, well, that's basically a flat surface, so it gets measured by its area, in square meters. Volume for the frame, area for the panel. Simple, logical, and totally universal.
Of course, buildings aren't just solid boxes. They've got openings, doors, windows, vents. So when you're calculating something like how much plaster you need, you can't just ignore those holes. And how you account for them follows some very, very specific rules.
So according to the IS 1200 code for plastering, there's this 3-tiered system. For really tiny openings, less than half a square meter, you don't make any deduction at all. And the thinking here is that the extra work it takes to plaster the tricky inside edges of the opening pretty much cancels out the material you save. For medium-sized openings, you only deduct for one side of the wall. And it's only for really big openings that you deduct the full area from both sides.
All right, you have absorbed a ton of information about the secret language of construction. So let's do a quick little pop quiz to help lock in some of those key ideas. You ready?
First question. The damp-proof course, that super thin layer that stops moisture from crawling up the walls, is it measured by volume or by area? And the answer is B, square meters. Because it's a thin layer with a set thickness, all we really care about is the area it has to cover.
Okay, next up, what's that magic number, that critical percentage that triggers a whole new budget review? If costs start to climb, at what point do you have to prepare a revised estimate? You got it. The answer is B, 5%. That's the official tripwire.
And for our final question, think back to that fine print. When you're plastering a wall that has a tiny little opening in it, what's the rule for deductions? The correct answer is A, no deduction is made. That's right. For those tiny openings, the extra work just balances out the material you saved.
So, there you have it. We've seen that every single building, no matter how big, doesn't start with a shovel. It starts with a spreadsheet. It's this whole world of careful rules, standard codes, and meticulous calculations. The next time you walk past a construction site, you'll know just how much planning came first. And that kind of leads to a final thought. Now that you know this hidden language, what story do the numbers tell you about the world being built all around you?